Good evening, ladies and gentlemen. My name is Mike Wooldridge. I'm here this evening in my role as Head of Department of Computer Science here in Oxford. And it is my very great pleasure to welcome you to our Strachey Lecture. The Strachey Lectures are our distinguished lectures in computer science. We hold 3 a year, and we felt it was very appropriate on this occasion to co-locate with the FLOC conference. And it's really wonderful to see Oxford full of so much activity related to the work that we do in Oxford. So the Strachey Lectures are named for Christopher Strachey, who was our first professor of computer science here in Oxford. And we have in the audience a rather impressive number of, for example, Turing Award winners, but we have one this evening with a very special connection to Christopher Strachey, and that's Dana Scott. Dana was for a long time a professor of mathematical logic here at Oxford and did some of the seminal work with Strachey back in the late 1960s and early 1970s. So Dana, it's really wonderful that you're able to be here this evening and give us this tangible link back to Oxford's past. So Dana was at Oxford for quite some time, and our speaker this evening was an undergraduate here at Oxford. So Stuart Russell, it's a very great pleasure to welcome you to give this evening's Strachey lecture. Stuart studied physics at Wadham College, just down the road, looking glorious in the summer sunshine this evening. He then went to California. He gained his PhD from Stanford University and then went to Berkeley in 1986, where he's been ever since. And Stuart's career is distinguished in a great many number of ways. He was the recipient of the Computers and Thought Award, and we have also in the audience the recipient of the Computers and Thought Award from the same year. So we've got an impressive number of award winners joining him this evening. Stuart's work has been on a number of areas in AI. He's well known for his work on meta-reasoning, his work on uncertainty, his work on machine learning. But tonight what he's going to talk about is one of the defining problems, I think, for AI in the contemporary era. And that is that there is the AI of symbols and logic and reasoning, and the AI of numbers. And how do we bring those two together? Everybody recognizes that they both have a role to play, but how do we bring those two together? So Stuart, it's my enormous pleasure to welcome you to give this evening's Strachey lecture. Thank you.
Thank you very much, Mike. It's a wonderful pleasure to be here and on such a beautiful evening. So I'd like to point out that a lot of this work obviously was done with my students, and in particular, it represents the PhD thesis work of Brian Milch. So I want to take you back to the 1950s when the field of AI was studying the question of how to build intelligent systems in the real world, and we really had no clue of how to do this whatsoever. It was a blank slate. We knew that people were intelligent, and what were we going to do to make machines intelligent? So John McCarthy and other people noticed a very important thing about the real world, which is that it has things in it. And that really matters. And because it has things in it, you need a mathematical basis that has things in it. You need the mathematics of things, of objects and relations. And for this reason, John McCarthy proposed that we build AI around first-order logic. This would be the mathematical framework. And this was a big departure. Up until that point, when you thought about robots or control systems, it was all continuous differential equations. If you were in statistics, it was linear regression and mixtures of Gaussians, things that seemed completely disconnected from first-order logic. So this was a big departure. So let's look at why first-order logic was chosen by McCarthy and why that choice had such a huge impact on the field. So the first reason is that logic provides a declarative substrate. So McCarthy's paper in '58 talked about an advice taker, a system that you could build simply by telling it the truth. Not by writing programs, but just by telling it the truth. And its decision-making would result from a process of logical reasoning and planning. So that was a huge step, right? In some sense, that was the precursor of the entire database industry, which is, again, about building systems in a declarative way. And we all understand, this is Flock after all, we all understand that declarative systems have many advantages in terms of modularity, the ability to combine and reuse information in lots of ways that weren't originally anticipated. First-order logic is also sufficiently expressive for most of the things that you would want a general-purpose intelligence system to do. And this expressive power is particularly important because without it, your models will not be concise. And if your models are not concise, then you will not be able to learn them from any reasonable amount of experience. So this is, I think, especially relevant now, and I'm talking to all you deep learning people who are not in the audience, because this is where deep learning is going to run into a brick wall in terms of the amount of experience you need to learn the model. So to illustrate this, let me just talk about chess. So chess is a very tiny part of the real world. There are just 32 pieces and 64 places, and the game lasts for about 100 steps. So it's really, really small compared to the real world. But if you try to write down the rules of chess in an inexpressive language, for example, if you try to write it using a hidden Markov model or an automaton, it's about 10 to the 38 pages to write the rules of chess. So you're never going to be able to learn the rules of chess in that form because you would need on the order of 10 to the 39 or 10 to the 40 games of chess just to learn the rules. So it's completely out of the question. And the states of your transition model, the states of the automaton or the hidden Markov model, would just be completely specified board positions thought of as tokens, right? There's no internal structure to this token. It's just a point in space that happens to be a chess position. So you might say, okay, well, we know better than automata. We can use circuits, or we can use graphical models, propositional logic. And in those languages, it's about 100,000 pages. You have proposition symbols like the white king is on square c4 at move 12. And again, that proposition symbol is an atomic token. It has no internal structure. And if you try to write down the rules of chess using symbols like that, you're going to have to write them separately for every square, for every time step, separately for each of the 8 pawns of each of the 2 colors, and so on and so forth. So again, you lack the expressive power, and you would need vast quantities of experience to learn those rules from examples. But in first-order logic, you can quantify over the locations x, y, the time steps t, the color of the piece, and the piece itself. And you can write rules saying that for every x, y, and for every time, and for every color, and for every piece, a piece of that color will be on that square at that time, if and only if such and such condition is true, which is mainly it was there before and didn't move, or it was somewhere else and it made a legal move to that square. And so in first-order logic, the rules of chess are about a page, about the same as they are in English. So this was a very good reason to use first-order logic, and a great deal of amazing work was done, particularly in the 1960s when we developed the first theorem-proving technologies. The Shaky robot project was based around first-order logic as its working language, and so we were able to demonstrate that you could in fact connect a symbolic first-order reasoning system directly to cameras and wheels and make a logic-based robot. Now, sometime around 1980 or so, people working in AI noticed something else about the world, which is that it's uncertain. And this puts a bit of a spanner in the works, as the English say, or a wrench in the works, as the Americans would say, if your approach is based on logic. Because if there is uncertainty about what you perceive, if there's uncertainty about the transition model of the world, then you are going to have a really hard time using first-order logic as your core operating language. And so within AI, mainly through the work of Yuda Pearl and others, we developed technology for parabolic reasoning, particularly parabolic graphical models, otherwise known as Bayesian networks. So let me talk about Bayesian networks, and in particular, the fact that Bayesian networks are really a propositional language. So a Bayesian network has random variables which correspond to the proposition symbols of a propositional language. So here's a piece of a Bayesian network from Yuda Pearl's book. So you may have an alarm in your house, and it may be caused to go off by a burglary or an earthquake. And we assume that burglaries and earthquakes happen independently, so there's no link between those two nodes in this model. So the structure of the Bayesian network represents independence properties of the domain, and then you quantify the Bayesian network by putting in conditional probabilities for each node given the parents in the network. So here I put in a prior probability of 0.003 of a burglary occurring, let's say in a 24-hour period, 0.002 for an earthquake. And then for the alarm sounding, if, let's say, burglary is true and earthquake is false, then there's an 80% chance that the alarm will sound. So it's a reasonably good detector of burglaries, not a particularly good detector of earthquakes, and so on. And the semantics of Bayesian networks is that these two things together, the topology and the conditional probabilities, define a joint distribution. So the probability of any particular assignment to those three variables is given by the product of the corresponding conditional probabilities from these tables. And so you can fill out that joint distribution as 8 numbers, specifying the probability of each possible assignment of values to the 3 random variables. And if you look at those possible worlds, right, marked in pink, you'll see these are exactly the same possible worlds as a propositional language. So Bayes nets are a way of, if you like, extending the idea of propositional logic to a probabilistic setting and allowing you to write distributions over those possible worlds in a concise way. So that was a huge step forward for AI, but it's still a propositional language and therefore limited in its expressive power. So back to our story. What do we think happened next? Well, the people working on logic noticed that the world is uncertain, and the people working on probability noticed that the world has things in it. And so, of course, you put these two things together, you get a first-order probabilistic language. This phrase, a new dawn for AI, came from an article in The New Scientist. There was actually a cover article in The New Scientist about the development of these first-order probabilistic languages and how important that was for artificial intelligence. And the article is called I, Algorithm, A New Dawn for AI. And as you can see, it says, at last, something else that thinks like us, which is complete rubbish, so I'm going to cross it out. But it was a significant step forward. So let me talk about these languages, which actually date not to 2011, but actually the mid-1990s. So you can combine the power of logical notation, which sort of separates the predicate from its arguments and allows you to quantify over the arguments. You can combine that with the Bayes net idea, which is how you represent a complex distribution as a product of factors, in a very straightforward way. And so you can almost imagine Bayes nets with sort of generalized symbols. So here we have not just a burglary in my house, but a burglary in any house. And so house here is a logical variable that ranges over all houses. And then we have earthquake not occurring at a particular house, but in the region, the geological region of a house. And then for that particular house, whether or not there's a burglary and whether or not there's an earthquake in the region of the house influence whether there's an alarm in that house. And this relationship holds for all houses. And so we have a quantified Bayesian network, if you like. So you combine that quantified Bayesian network with background information about what are the houses and what are the regions that those houses sit in. So you have region A with houses 1 and 2 and region B with houses 3, 4, and 5. And then you basically ground out the quantified Bayesian network by instantiating it in all possible ways with the houses and the regions, and you get a traditional Bayes net with ground propositions, and then you can run traditional inference on that. So this is how these languages worked, essentially by converting the generalized model and the skeleton, the relational skeleton, the facts about the objects that existed in the world, to produce a Bayes net that you could then run inference on. And you get some cute things. So this is the grounded Bayes net with the two houses in region A and the 3 houses in region B. And if you observe whether or not the alarm sounds in those houses, so you have one house, the green house in region A, and then in region B you have the 2 houses, you actually discover that there's probably an earthquake in region B, because that's a much more likely explanation for 2 houses having alarms sounding rather than just one. And so with that very, very simple model, you've actually built a distributed earthquake detector using burglar alarms. Okay, so you might say, well, look, this is such a straightforward idea. Why did it take so long, right? Why didn't we just go straight from the realization that the world is uncertain and has things in it to first-order probabilistic languages? We could have done this in the 1970s or something like that. I'm not sure why it took so long, actually. I think it's, to some extent, because of the unnecessary separation between the communities that deal with logic and the communities that deal with numbers and probability. And I can remember as a graduate student at Stanford, we were taught that probability was a bad thing, right? You don't want to know anything about that because, your mind will be corrupted and it can't possibly work for AI, so do not learn probability. Now, yeah, so theoretically this could have happened. In practice, it took much longer than necessary. But actually, there's more to it than that. Because when you combine uncertainty and things, something interesting happens, which is that not only does the world have things in it, but you don't know what they are. And so this approach based on these probabilistic quantified Bayesian networks with a known relational skeleton where you know what the objects are and you know what regions the houses sit in and so on, so you know the relational structure, that cannot work in general. For some specific applications it can work, but in general you're not going to know what exists. And so that means you can't use those approaches. So that leads to the work that I'm going to talk about on open universe probabilistic languages. So I want to explain what I mean by open universe. And many of you will already be very familiar with this distinction. You may know it under other names. But the distinction between closed and open universes is something that actually went almost unnoticed in many of the early AI textbooks. And in fact, people wrote down, in explaining how to use logic to do knowledge representation, they actually wrote down a lot of extremely incorrect sentences because they were assuming that they were treating first-order logic as if it was a closed universe language. So they forgot to write a lot of the closure conditions, whereas, in fact, of course, as you know, first-order logic is an open universe language. So let me make this clear. So first of all, a closed universe language is one that assumes the unique names assumption so that every object has a distinct name, and then domain closure, which is that there are no objects that are not named by symbols or terms in the language. And Prolog makes this assumption. Databases make this assumption. Sometimes it's called Herbrand semantics for Prolog. Lots of statistical packages use a form of quantification. They call it indexing, but the indexes are enumerated and have a fixed range. And so they're saying, I know all the random variables, 1 through 100 that exist. So again, a closed universe kind of representation. And as I mentioned, these early first-order probabilistic languages. Whereas with open universe languages, you can be uncertain about what objects exist and about their identity. So you can have multiple names for the same object, and you may not know whether 2 names refer to the same object or not. So first-order logic has that property. The language I'm going to talk about, the blog language, is an open universe probability modeling language that has this semantics. And then there's a large class of what we call probabilistic programming languages, where you define complex distributions over the execution traces of a stochastic program. And so I'll illustrate the idea of a probabilistic programming language later on. And you can think of Blog as a declarative probabilistic programming language in the same way that Prolog is a declarative programming language. So I'm going to test you to make sure you understand this distinction. Okay? So let me ask this question. If I tell you that Bill is the father of William and Bill is the father of Junior, the question is, how many children does Bill have? Okay, so hands up, people who think 2. Right? Hands up, people who think 1. Hands up, people who are not sure. Okay, I think that's the rest of you, lots of you. Okay, well, so it depends who you ask, right? If you ask a database system, then the answer is 2, right? William and Junior. And there are no others, right? Because it's closed, it's a closed universe. If you ask first-order logical system, the answer is anywhere between 1 and infinity, right? Because William and Junior could be the same person. In fact, they probably are in this case. And there may be other children that we simply didn't mention. And so, because in the real world, we so often do not know in advance what all the objects are and what the relational structures are that relate them, we're going to have to use open universe languages. You think about language, right? Before you open the book, you don't know who all the people are, right? When you come into a room, before you come in the room, you don't know who the people are that you're going to see. You don't know what chairs there are going to be. You don't know what's going to be on the ceiling, right? So you have to have a priori uncertainty about existence. And that's going to be crucial, I think, for many real-world applications of AI. So let's just illustrate the consequences of this distinction when we think about the model theory, right? Because we have to talk about what are the possible worlds and how we're going to put probabilities on them. So let's take almost the simplest possible case, right? We have 2 symbols, A and B, and 1 relation symbol. So in the closed universe, right, every world is going to have exactly 2 objects, right, which are called A and B. And so we might as well think of A and B as actually being in the world itself. So the possible worlds only vary in how A and B are related by the 1 relation symbol that we have. And in fact, there are exactly 16 worlds, and they're all the same except that they vary in what the relation is itself. So the objects are the same in every world. Now, in the open universe, as I said, it can be between 1 and infinity objects. If there's 1 object, then it has to be called A and B, right? If there are 2 objects, then one of them might be called A and B, and the other one might not have a name. Or one might be called A, the other one might be called B, vice versa. So there's a much more complicated set of worlds, and there can be objects that are neither A nor B, and there can be arbitrarily many of them. And so you have infinitely many possible worlds of different sizes and shapes and complexity. And so the obvious issue then is, how are we going to specify a probability distribution over all of those worlds and do it in a well-defined way, right? Remember, probabilities all have to add up to 1. So we have to specify infinitely many numbers, and they've got to make sure they add up to 1, and they have to make sense for all these worlds of different sizes and shapes. So that's the challenge we face. So how do we do that? Well, we went back to the way of thinking about Bayes nets as methods of constructing possible worlds. So when you look at a Bayes net, you can think about it as, okay, it represents a joint distribution as this product of factors. Or you can think of it as a machine for producing possible worlds by a sampling process. And these are entirely equivalent ways of thinking, just one is more helpful for this case. So when I want to use a Bayes net to sample worlds, I just start from the beginning, and I pick a value for any of the root variables. Let's say burglary is true, and earthquake is false. And now I sample alarm conditioned on burglary being true and earthquake being false, and let's say the alarm sounds. So now I've made a possible world, and the probability of producing that possible world is exactly the probability specified in the joint distribution. So how am I going to make these more complex worlds? So it turns out that we need two kinds of steps. So the first kind of step is essentially the same as it is in Bayes nets. We're just fixing the truth or falsehood of some event variables based on event variables whose values are already fixed. And so in the first order language, we have to specify, for example, for alarms in houses, how do alarms in houses get their values? Well, it depends on whether or not there was a burglary in the house and whether or not there was an earthquake in the region of the house. And so this is just the sort of quantified version of Bayes nets that we already saw. But we also need to get houses and regions into the world, right? So where are they going to come from? And we use what are called number statements, basically to say, look, the world is going to have to be built up step by step from objects, and we're going to do it in some causal order. And we'll start with, in this case, the geological regions. They came first. And so just a priori, there's somewhere between 1 and 10 regions. And then for each region, there's going to be some number of houses. And let's say Poisson with a mean of 50 for the number of houses in each region. Okay? And so these steps add objects to the world. And every time you add an object to the world, you're then adding more random variables to the world because that object has to have properties and relations to other objects. And so the world gets built up in these sort of complex interleaved set of steps where objects and properties and relations get added in some order. And the blog program essentially tells you what those steps are, and the topological order of the blog program tells you how the ordering of construction would happen if you were to use it to construct things. I just want to mention one piece of terminology. So I said that the number of houses in each region is Poisson of 50. So the houses are sort of, as it were, generated by the region, and we call the region the origin function of the house. Okay, so every house that think of it as a mathematical object that's defining the possible world is going to have an origin which is some particular region. Okay, so this is intuitively how we use the language to specify distributions over this very complex set of worlds. And to be more precise, the semantics works as follows. So the objects in this formal language, the things that go in the worlds, right, are actually more complex than they typically are in first-order logic. In first-order logic, they're usually either just arbitrary tokens. You can think of them as just the integers, or tokens labeled by integers. Or in a typed language, they would have a type and then an integer label. But here, we actually define them by both a type and a number, but also the origin. So the origin is whichever object it's assumed that was responsible for this new object being in the world. So geological fault regions have no origin, and so they just have a blank origin field, and this is the third geological fault region. But then houses have a region that produced them. So this is the 97th house in the region, which is the geological fault region number 3. Okay? And so those are the formal objects that populate the possible worlds. And then the basic random variables, so out of which we're going to then construct the probability distribution, are all of the functions and all of the predicate symbols applied to all possible tuples of objects. Okay, so earthquake is a unary predicate, so it has one argument, which is a region. So there's a basic random variable for is there an earthquake in geological fault region number 3. Okay, and that random variable is true or false in any particular possible world omega. And then, right, so to make a whole possible world, you just have to specify values for all of those basic random variables and all of the number variables which define how many of the basic random variables there are. And once you've done that, then you have a very nice, simple way of defining the probability of a possible world. It's just the product of all the conditional probabilities in the blog model that went into producing that particular world. Okay? So the reason this works, this just repeats that statement, is because we made the objects in the world contain within them their generation path. And that generation path is unique for any particular object. So no two objects are going to have the same generation path. And so, so that means there's only one way for that possible world to be generated. The right sequence of sampling events has to take place through the blog model in order for that world to come into existence. And there's only one way that can happen. And so its probability is just the product of all the required events taking place. Okay? Now, if we use standard first-order logical semantics, then we would have worlds containing objects just like O1, O2, O3, and there would be some arbitrarily complex combinatorial formula for how many ways that world could be produced by following some sampling path through the program, and it would be much more difficult to specify the semantics and inference. So you could do it this way. I'm not saying it's impossible, it's just that the other way turns out to be much more clean and simple, straightforward. So from this, we get a very nice generalization of the Bayes-Net theorem, which says that every well-formed blog model specifies a unique distribution over all of the possible worlds that you can define based on the signature of your model, so the predicates, the function symbols, and the constants. Now, for this to be true, just as with Bayes-Nets, they have to be acyclic. For this to be true for blog models, they have to basically be non-looping. So you're not allowed to have infinite receding ancestor chains, and you can't have dependency cycles that can be satisfied in the program. And you have to do a few other things, so you can't easily prove Fermat's last theorem automatically, because Fermat's last theorem says something about infinitely many objects, and so there are various other technical conditions that have to be satisfied. Okay, so now I want to illustrate some uses of the blog language, because that's what really matters. It's not about how much math we can do. It's whether the math turns out to be useful, that it corresponds to any real model that you might want to write about the world. So here's a problem, which if you've ever used Google Scholar or Quora or any of these other citation engines, underneath, this is the core problem they are solving. We have two citation strings here, Lashkari et al. 94, collaborative interface agents by Yezdi Lashkari and Max Mitral and Papi Mays, blah, blah, blah. And then another one, Mitral M. Lashkari Y and P. Mays, collaborative interface agents in Conference of the American Association for Artificial Intelligence. So how many people think that those are in fact referring to the same paper? So here, this is a forced choice, right? You can't sit it out. I need you to choose. Okay, who thinks it's the same paper? Okay, who thinks it's a different paper? Okay, we have a slight majority in favor of the same paper. That's part right. These are in fact the same paper. Probably the second one got messed up because someone put a comma in the BibTeX field in the wrong place, and so the names of the authors got messed up. And if you're an AI person, you know that the AAAI conference is what's sometimes called the National Conference on AI. And you also know that MIT Press is in Cambridge, even though the conference itself took place in Seattle. So you can have a good understanding of how these two things came about, but they are in fact the same paper. So this question is answered billions of times a day by these citation engines that serve your queries every time you ask for some research, some literature search question. So given a whole collection of these citation strings, which are scraped out of PDFs that the system finds on the web, the goal is to find out, okay, what actual papers exist? What people exist? Who wrote which paper? What was its title? Which paper cites which other paper? Right? So you're trying to extract a relational database from something which just consists of strings of ASCII. Right? There are no objects here. There are no authors. There are no venues. There are no paper titles here. There are just strings of ASCII. And the system has to figure out, from all this ASCII stuff, an actual relational database. So you might think, oh, goodness me, this is a really complicated problem. But if you think about it as an open universe inference problem, it turns out to be fairly simple. So here is a slightly simplified version of a blog model. So the main simplification is just to have a single author paper, so we don't have to worry about lists of authors. So this is the blog model. I'm going to go through it piece by piece. So first of all, the number statements that say what are the things in the world likely to be. Okay, so OM is order of magnitude. So this says there are about 100,000 plus or minus a factor of 10 researchers, and then the number of papers whose origin is a particular author R is either about 100 if it's a professor, or about 10 if it's an ordinary person. Okay, this is just for the sake of illustration. And so this describes the sort of the basic contents of the universe. Now, these objects are going to have some properties. So authors will have names, and we don't know what they are. So we'll just have some name prior, which is actually a letter trigram prior over names of authors, which was learned from a census database. And then papers have titles. And those titles, again, we don't know what they are, but we'll have a combination word and letter trigram prior drawn from a big database of computer science papers. And now the citation strings themselves. Okay, so first of all, a citation cites some paper. Again, we don't know what it is, and a priori, we may as well just assume that it's drawn uniformly from the set of papers. Now, we could have a more refined model that says you're more likely to cite famous papers. We could also add time into the model and say you can only cite papers that existed already at the time you were citing, and that would make it better, but this is a simple model. And then the citation string itself, the text of the citation, is produced from, I'm sorry, this is at the bottom of the screen, so I'm going to read it out, from the name of the author of the cited publication and the title of the cited publication. Now, and then that information goes through a noisy citation grammar. So there's all kinds of ways you can spray that information onto the page in the form of an ASCII string. You can make spelling mistakes, you can abbreviate the author or not, you can mess up the sequence, you can put the wrong title or leave out a word, or any number of other ways you can mess it up. And notice that, of course, we don't know for this citation who the author is. We don't know which paper is being cited. We don't know the names of any of the authors. That doesn't matter, right? That's up to the inference engine to figure it all out. So this is the citation information extraction engine, in brief, right? You just describe how this data came into being, because there were people, and people wrote papers, and then the papers got cited by some messy procedure. And then you write that model, you supply the data, just all the raw data strings, ASCII. You then ask a question, whatever question you care about. What papers exist, who wrote them, what's the citation graph, whatever you like. And then you run inference. And if you use the generic inference engine that comes with blog, it will work, but it'll take a long time. So typically for these large-scale applications, we have to do some work to make it run fast enough. So this just shows the results. So we tested on a database for the CiteSeer engine. For those of you who've been around long enough, that was the first big citation engine before Google Scholar. And they conveniently produced 4 benchmark data sets, and they measured how often for papers in those data sets they were able to extract exactly the set of citations that belong with that paper. So you couldn't accidentally cite another paper and put it in that set, and you couldn't leave out any of the citations that referred to that paper. So how often are you getting the citation for a paper exactly correct? So it ranges in this data set from about 6% for a data set about face recognition to 20% for reinforcement learning papers. And then with the blog model that I just showed you, we reduced this by between we reduced the error rate by between 2 and 3. And this actually only takes about 15 minutes to run, so it's relatively practical. So after this, we actually wrote a whole lot of other models. So many standard machine learning models. So things like PCFGs can be written. You can have the standard statistical species counting model very straightforwardly with a sort of a ball and urn model. You can have the latent Dirichlet allocation topic models. You can make infinite mixture of Gaussians. You can do Kalman filters and all kinds of other things. And all of these are 3, 4, 5 line blog programs with no math, right? If you don't like math, this is great because you don't have to do any of the math, right? You just write the model and all the math is done for you by the inference engine. A few more sophisticated ones, citation information extraction I already mentioned. So Sybil attacks in the cybersecurity where people use multiple login identities to fool a reputation system by recommending each other very highly. You can think about detecting the kinds of patterns of recommendation behavior that would reveal that there was a Sybil attack going on. Multi-target tracking is what radar systems do when they need to keep track of many objects using intermittent detections with a noisy radar signal. We can also extend this to decision making. There's a lot of interesting questions that arise when you start doing uncertain decision making in a first order language. So we had fun with blind monopoly, where you can't see where your opponent is, and the only information you get is every so often you have to pay rent when you land on something that you weren't expecting, and every so often you receive money that you weren't expecting, and then you have to figure out what's going on, and the inference engine was able to handle this pretty well, and actually to construct very effective policies for that game. So I'm not going to talk too much about inference, except to say that subject to the usual technical conditions that we have to assume for convergence for sampling algorithms, we have 3 complete algorithms for any well-formed model in blog. So rejection sampling, importance sampling, and MCMC, Markov chain Monte Carlo. And MCMC is the one we use most often because it's actually much more efficient for lots of real cases. And so as long as you can evaluate the query on each world that you visit, so that rules out Fermat's last theorem, unfortunately, as long as you can evaluate the query on each world that you visit in the sampling process, then you will be able to answer that query eventually. And the algorithms all work by effectively grounding out part of the model, the least amount of model that has to be grounded in order to have a well-formed fragment where you can calculate the probability of that partial world. And then as the algorithm runs, that grounded fragment grows and shrinks as you could add objects to the world, you can take them away, you can connect objects with relations or remove those connections, and all of these changes cause the model to grow and shrink. And we'll see examples where it's producing models with more than 1 million variables simultaneously in memory and running. So you can think of these as deep networks with 1 million nodes, if you like, but their structure is changing millions of times per second, and probability calculations are being done all the time. So let me skip over. There's a number of reasons why MCMC has advantages, but I think I'm going to skip over that. And I wanted to talk about probabilistic programming because it's a very hot area now. There have been several workshops at Popple, and there's now going to be a full-scale probabilistic programming conference in the fall of this year. So I recommend people attend that if they can. So what's the basic idea of probabilistic programming? In principle, it's a very simple idea. It says, take an ordinary program and put in random choices. So flip a coin, make a Boolean random choice or a continuous random variable between 0 and 1. So as the program executes, it can make different choices depending on how these coin flips come out. Right? This is something people use all the time. These are ordinary randomized algorithms. But think of the randomized algorithm as defining a probability distribution over all possible execution traces given the inputs to the program. And when you do that, you can then think of using it to do probabilistic inference. For example, if you run lots and lots and lots of executions, you can say, well, in what fraction of those executions did a burglary take place? Right? And now you're actually using it for probabilistic inference. And so because programs during their execution can construct objects, and by making random choices, you can decide to construct an object or not, you actually have uncertainty about what objects exist, okay, or what data structures get built during the execution of the program. So you can use PPLs to represent open universe probability models. Now, that's pretty much all they do for you, right? So they don't necessarily provide a declarative language to represent the world about which you want to reason. You have to build the data structures. So here's in the scheme language, here is the same probabilistic program that we just had for earthquakes and burglaries and regions and houses. So the blue part actually looks quite a bit like what we would write in the blog language. So we've got, if you like, a number statement saying that there's between 1 and 3 regions, and we have a number statement for the number of houses in each region. And then we have down here a definition of effectively the Bayes net for any particular house in any particular region. But in addition, you have to define the data structures that are going to then receive the values as all these coins are flipped. You have to record the values of whether or not there was a burglary in that house or whether or not there was an earthquake in that region. So you also have to define the data structures to contain the contents of the world that you're constructing by this random process. And so I think that by providing a declarative language, the same argument why we use databases, same argument why we use logic programming, by providing the facility for constructing worlds, representing them automatically, a declarative language maybe has some advantages. Okay, so there's a number of things that we've done to make inference efficient, and there's nothing particularly amazing about any of these. In practice, we often have to write application-specific proposal distributions to make the MCMC run fast, and we've shown that you can actually have proposal distributions that learn how to randomly explore the space of worlds so that they converge more quickly. Probably the most effective thing we did was actually to realize that there's a notion of compiling that you can apply to probabilistic inference that largely went unnoticed for the last 30 years or so, since we started writing Bayes net algorithms. Effectively, what you realize is that a Bayes net is a data structure which is not going to change while inference is running. So what on earth are you doing continually consulting the same data structure to find out, okay, what is the parent of this variable, what is the child of this variable, what's the conditional probability for this variable given its parents? All that information is fixed, and therefore you can compile out all of that overhead and write automatically inference code that works for that specific model. And just as Prolog compilation gives you a 200-300-fold speed up, we get the same speed up for compiling probabilistic inference. And in fact, when we compared it to bugs, which is the most widely used of the Bayes net packages, even though blog is, it's an open universe first order language as opposed to a closed universe propositional language, we are actually running about 700 times faster than the bugs package on the same models. So, okay, I'm going to skip through some of this. So there's interesting work going on at MIT on parallel implementations of inference on special purpose chips to run this kind of inference really fast. There's a lot of interesting work on lifted inference, which is the analog of doing resolution theorem proving as opposed to converting to propositional logic and using a SAT solver. And it's very elegant, it's very beautiful, but so far it hasn't resulted in any speed up on any interesting model whatsoever, because as soon as you have observations, all of the variables become different and you end up having to treat them all separately one by one, and you don't get the speed up that you hope for. So I still hold out hope for that approach, but it remains to be seen whether it's really going to be feasible. So this just shows you some of the results. And I should mention that there are other compilers now. So Microsoft has a language called infer.net, and they put a great deal of effort into compiler technology for that. And they actually use that for a lot of online user-facing tasks with millions of queries being run every day. For example, if you've ever used TrueSkill, which tells you how good you are at some particular online game, that's running basically a giant first-order probabilistic inference calculation. So let me talk about some of the applications. One has to do with nuclear testing. So in the history of the world, there have been at least 2,055 nuclear explosions, which was a bit of a surprise to me. I didn't think it was that many. But so 2 of them in Japan killed about 200,000 people. And then the tests, right, which are just tests, right, these are scientific experiments, killed another 100,000 people from dumping fallout into the atmosphere in vast quantities. So here's a crater from a very small nuclear test in Nevada. This is 12 million tons of rock and earth that was ejected into the atmosphere from a small nuclear test. The biggest test was 500 times larger than this one. So the scale of these things is, even though, of course, we know intellectually that they're really big, the scale is just unimaginable. So there's a treaty called the Comprehensive Nuclear Test Ban Treaty, which aims to ban testing. And of course, it has a verification regime designed to detect anyone who's cheating. And so the evidence for this problem is collected from something called the International Monitoring System, which is about 150 seismic stations that are spread all over the world, along with infrasound, which is very low frequency sound in the atmosphere, and then hydroacoustic stations, which detect vibrations in the ocean. And so that data looks, the seismic data looks like typical seismic squiggles, right? So this is the evidence that we have. And then the query is, what happened, right? So you collect all these squiggles from stations all over the world, and you produce a bulletin, so a daily bulletin saying, these are the seismic events that took place, their locations, their magnitudes, the time, the depth, and then you also flag the ones that are suspicious that might be man-made seismic events. And then the model is basically what we know about geophysics. So we know a lot about the natural occurrence of earthquakes geographically. We know a lot about signal transmission through the Earth. We know something about velocities. We know the different types of signals that are propagated through the Earth. We also know something about how those signals are detected by the seismic stations, and then something about the level of noise that's in the background all the time. So just to give you a picture, this is a magnitude 6 event that took place near Japan, and it was detected. This is a station that's 9,724 kilometers away, and this is the signal that arrived at that station. And this shows the easiest thing to see is the first arriving phase. So phase is the name that geophysicists use for a particular type of wave that is produced. So the P phase arrives, and then later on, the S phase arrives because it has a slower velocity and takes a slightly different path through the Earth. And on this scale, we're looking for events that are about that big, right? So we're looking for the tiny little bumps that could be a nuclear explosion that someone is trying to hide underground. And so it's not as easy as you might think to detect nuclear explosions, even though they seem like enormous things. They can be hidden underground. They can be engineered in such a way that the ground itself will damp the waves coming out from the explosions. So let me tell you what it is we know about geophysics. It's not that complicated, right? First of all, there are seismic stations, and we know where those are. And then a seismic event is going to occur somewhere. We don't know where. Let's say it happens here. A seismic event occurs, seismic wave propagates out, it reaches a station, and causes some blips to appear, right? And here we see 2 blips coming from this event at that station. Now another event occurs, the blue one, and waves go out from that, and that causes more blips to appear. And notice that because the blue event is much closer to that top green station, its blip appears before the red blip, even though the blue event took place after the red event. So this is like having 1,000 conversations that are randomly scrambled into an arbitrary order and then trying to decipher those conversations. And of course, even though I've shown the blips as red and blue, the blips are not actually colored, right? You have no idea which event produced which blip. So you have identity uncertainty, right? There are blips, and they could come from the same event, or they could come from different events, and you don't know. So you don't know how many events there are. All you know is how many blips there are. Many of those blips may be false blips that are not produced by significant seismic events at all. So that's the nature of the problem, and magnify it by 30 times as many stations and about 1,000 times as many blips per day, as I've shown here. So here's the model. Again, it's not particularly complicated. And this is the global monitoring system for the Nuclear Test Ban Treaty. So I'm going to just show you a few pieces of it. First of all, the number statements that say what objects are going to populate the world, right? There are going to be seismic events, and the number of seismic events in some particular time period t is a Poisson distribution with some rate lambda. And so that's how many events we expect to see in a fixed time period. And then there are detections, so those blips that I showed you on the graph. And there are 2 kinds of blips. There are blips that come from seismic events, and that's the second line. The number of detections coming from an event E with phase P, that's the type of the wave, at station S, is either going to be 1 if you detect it or 0 if you don't detect it. Okay? And then there are also noise blips, right, that don't come from any particular event. They could just be from waves crashing on the shore, or trees falling over, or ice cracking, or all kinds of garbage that happens at these seismic stations. And so they occur with some Poisson rate as well. So those are the objects. The location of an event depends what kind of event it is, right? So if it's an earthquake, then it's going to come from some natural seismicity spatial prior that we can estimate from historical data. If it's a man-made event, the treaty requires us to assume that it's uniformly distributed over the entire Earth, right? We're not allowed to assume that it probably came from North Korea or Iran, because Iran is a member state of the treaty, so they are not going to allow people to pick on them and target the monitoring at Iran. So we have to assume that it's a uniform distribution over the Earth. Okay, so that's how we write that part. This is the spatial prior, which is estimated from historical data. That's part of the blog program that I didn't actually show you. The probability that an event is detected is a logistic function of the magnitude of the event, the depth of the event, and the distance from the event to the station. Right? This all makes perfect sense, and you can just write it directly in the blog language like that. Okay, and here's the detection probability. So for a P phase in Alice Springs from an event of magnitude 3.5, the model predicts a certain detection probability as a function of the angular distance from the event to the station, and then the empirical data fits that distribution pretty well. An S phase is much less likely to be detected from a small magnitude event like that. And then when does the blip arrive? Well, it depends on how far away it is, right? So the travel time depends on the distance from the event to the station, the depth of the event, the phase, which is what kind of wave is being propagated, plus some Laplacian noise, it turns out. And here's empirical data showing that the uncertainty in the travel time prediction is Laplacian. And then we can evaluate that in the usual machine learning way. You train on some historical data, and then you predict unseen data in the past. And we showed back in 2011 that our system was between 2 and 3 times more sensitive than the existing detection system that the United Nations was using. And then, so after a while, we convinced the United Nations that, in fact, these results were real and it really was working well. So in 2014, they announced that NetVisa would be the official monitoring system for the treaty. And then it took a little more while until January of this year when it actually went into service. So it is now running in Vienna and monitoring the Earth for earthquakes and explosions. So here's one example from the North Korean explosion in 2013. So this is a satellite image of the general region where we think the event took place. The green triangle is the location estimated by essentially a meeting of all the world's geophysicists who got together, examined all the data, did their best to estimate where the event took place. This is the location that NetVisa estimated, and then this was later on found to be the tunnel entrance for the testing facility. So we were only about 700 meters away from the tunnel entrance based on sensory information coming from thousands of kilometers away. Okay, I'm going to very quickly go through a couple more examples just because I want people to understand that we are not building seismic monitoring systems, right? We built the blog language and then we write models that allow you to solve these problems effectively. So I thought it would be interesting to see if we could do computer vision. There's a particular probability model used in computer vision, which is called adaptive background mixture model. It's used for tracking moving objects in video. So it generalizes the old idea that you can sort of average, I can take a picture of this room for 24 hours with a camera. Over that period, the fact that you came in and left and moved around and so on will all be washed out. And I will just get an empty room if I wait long enough and average that signal. And then I can take that empty room and I can subtract it from the current image to get a picture of all the objects that are in the room and moving around. So that idea has been known actually since the 19th century. There's a famous picture of the Charles de Gaulle Étoile roundabout in Paris, which is always full of vehicles, but if you wait long enough, they all disappear in the average background image. So this is a probabilistic version of that. And we wrote this model in '97, and we showed that it worked, and it became part of the standard armory of computer vision. But we wanted to do something much more sophisticated, right? So what the model says is that at every time step, so in every frame, each pixel of the image samples its value either from the background, which is the sort of the constant value for that pixel, or there's an object obscuring that pixel, so you sample from a foreground distribution, or it's in shadow. So at every time step, every pixel chooses whether it's background, foreground, or shadow, and the background value is specific to that pixel. And then, as you get the data, you estimate the mixture parameters for that model. So what we wanted to do was actually to implement a more complex model with temporal persistence, where if a pixel was in shadow, it was likely to be in shadow in the next time step as well. And we also wanted to have spatial contiguity. So if a pixel was in shadow, it's likely that the neighboring pixel would also be in shadow. But the thought of trying to do all the math to make that happen correctly and then write all the code to implement these improvements to our model was that was too much for us, given that we weren't really computer vision researchers anyway. But in blog, you just upgrade the model very simply. So this is the basic model showing that the intensity of each pixel is sampled from a mixture model at each time step. And if you want to implement temporal persistence, you just say, well, it's sampled according to some transition model from whatever state it was in at the previous time step. And you don't do any math, right? So you don't write a whole journal paper on an improvement to the background adaptive mixture model algorithm with a whole bunch of probability equations and calculations and theorems and proofs. You just modify the model and then you run inference. So here's the original model running, and you can see it kind of works, but there's an awful lot of noise pixels which are not moving objects, but being detected in the windows and the trees and on the road and so on. And then here's on the right, the improved model, and it really works fine. On the left, this is the OpenCV, which is a standard computer vision package. It actually has some serious failures on this data. So you can do computer vision, at least of a simple kind. You can also do natural language understanding. So this is a natural language understanding program. So I'm going to turn it into English so that you can read it. It says, okay, there are lots of objects in the world. There are quite a few relations in the world. Relations are expressed by strings. Don't know what they are. Relations are applied to objects, but they're fairly sparse, right? So this is a key assumption, it turns out. So we don't know which objects exist. We don't know which relations exist. We don't know which objects are related to which other objects, but we do know that relations tend to be sparse. So out of the things that are true, the relations that hold, people choose some of them to say, and then they say them. They say those facts by taking the first argument of the relation and the second argument of the relation and the verb that represents the relation and putting those together into a sentence. So that's the model. Right? Notice this doesn't talk about any particular language or any particular world, doesn't make any assumptions. So you can just provide text in any language, actually. Here we provided text from the New York Times, from Andrew McCallum's group. So you have, it's restricted to simple sentences like J. Edgar Hoover, who was director of the FBI, so named entities that are related by some relation. And then you simply ask, so you provide a bunch of text and then you ask, okay, what's true? That's it. And so we run it on about 10,000 sentences of New York Times text, and it finds relations, and it finds how those relations are expressed in text. So here's relation number 46, and it's expressed in 16 different ways in the New York Times. So unit of, part of, subsidiary of, owned by, parent. So you get the sense that this has something to do with one thing being a corporate subsidiary of another. So it discovers that this is a relation that exists in the world and how it's expressed in text. And then it pulls out facts. So here are about 40 facts describing subsidiary relationships among corporations from the New York Times. Okay, so to summarize then, I think that unifying logic and probability is a fruitful area, and importantly, it introduces this new kind of uncertainty about what exists and which object is which. And we call these open universe probability models. And if you have the ability to reason with these kinds of models, then you can learn about what exists from raw data that doesn't contain any objects intrinsically. The data is produced by objects, but they're not identified in the data. It also allows you to use prior knowledge. So we saw how to apply knowledge of geophysics so that you could very effectively learn from historical data to produce a monitoring system, for example. And we can, I think, try a very wide range of applications. So there's a lot of unsolved problems. To me, the biggest one is how you answer questions against a very large body of evidence. So imagine that the evidence you're interested in is everything on the World Wide Web, right? The entire contents of the web. Now, Google answers questions with respect to that body of evidence 1 billion times a day. How do they do that? They do it by pre-processing and computing all these indices, which allow them to then answer queries extremely fast. So what's the analog in the case of probabilistic inference? It would mean taking the whole web, pre-processing it, and producing a posterior distribution over what the real world contains, right? And then answering questions with respect to that posterior distribution efficiently. So that's a mammoth undertaking. And how you would represent that posterior distribution concisely enough to store it in memory is really an open question. I think the answer is you can't, but you can use it to pre-compute a large number of low-order statistics about the world, which will allow you to answer most queries efficiently, and you're still going to have to use additional inference for some queries. Okay, I think I'll stop there. Thank my funders in the usual way, and thank the audience. Thank you.